Okay, this is part 2 of integration by parts. Okay, so I have an example that I wrote out ahead of time because I didn't want to make you sit there and watch me write this because I didn't want this to go too slowly. But here's the formula for integration by parts. Here's the standard advice for what we make u. And here I have an example. I would like to integrate x squared sine x. Okay, so let me try to get through this fast because I'm going to do this, and the way I'm about to do it is really not the best way, and then I'm going to show you a better way right afterwards. But in order to appreciate that this isn't the best way, let's go through it first. This will work, it's just not the best way. So I have my priorities for u, so I go down the list. I don't see any logarithms. I don't see any inverse trig. I do see trig, but I don't see inverse trig. I don't see arcsine. I do see a power of x, so that's what I'm going to make u. U is x squared. dv is the rest, so dv is sine x dx. I find my du, so that's 2x dx. I find v, of course the antiderivative of sine is negative cosine. Many people would miss this negative, but that it should be there. The derivative of sine is cosine, the antiderivative is negative cosine. But okay, so we do integration by parts. So I go u times v, and that's here. And then I subtract the integral of v du. So I subtract the integral of, here is v and here's du. Okay, so I'm here. I clean this up a little bit. Of course, I can pull the negative sign out. I can pull the 2 out. And so this turns into this. So it's a plus 2, and then it's the integral of x cosine x. And as usual with integration by parts, we just have to hope that the new integral is something that's easier to do. And it's, well, I don't know, is it? This is not something that's on the list of antiderivatives that I have memorized. I don't have x times cosine x on the list. What I can do to this is I can do integration by parts again. So let me explain why this is better, and hopefully this doesn't result in us just doing integration by parts again and again and again forever, because we already did it. But we are making progress, and let me explain. The original integral had an x squared, and the new integral has only x to the 1. And basically, if I do this again, that's going to reduce the power again until it's x to the 0, which is just 1. So by repeatedly doing integration by parts, I can keep reducing this power of x until it's gone. So that's what's going to happen. So I just underlined this part, and I want to just work on this part. And then when I come to my final answer, I'll have to put this all together. But for right now, I'm just going to figure out this part. So I go down here, and I'm going to do integration by parts again. So I'm going to use the letters u and v again. They're not the same as the u and v from up here, but we're done with this u and this v. We're done with it once we get to this point. So I'm comfortable just using the letters u and v again. So I look at this, and I run through my list of priorities again. I don't see any logarithms here. I don't see any inverse trig. I do see a power of x, which is this x. So u is going to be x, dv is the rest, so it's the cosine and the dx. du is just, well, derivative of x is 1, so du is just dx. v is the antiderivative of cosine, which is positive sine. And then, so I do integration by parts. I have u times v, so that's x times sine x, that's here. And then I subtract the integral of v du, so that's minus integral of sine x, and then du is just dx. Okay, we've done integration by parts twice now, and as I discussed, there is no more power of x here. It's like x to the 0, or just, we just don't see anything because it's like 1. And this is on my list. This is something that I have memorized. The antiderivative of sine is negative cosine, and then the minus cancels this, so it turns into a plus cosine. Okay, and then we just have to put our answer together. So I go back up here, I write minus x squared cosine x, that's there, and then plus 2 times this thing that we just figured out. So I go 2 times the answer that we just got. So I put this here. And then I distribute the 2, and that's it. Okay. But like I said, there's a faster way. When you're in a situation where you anticipate doing integration by parts multiple times like this, like we see an x squared, and we anticipate having to do integration by twice, because like each time we do it I get rid of an x, and there's 2 x's, so I want to get rid of them, so I'm going to do it twice. There's a shortcut for that. So this shortcut is called tabular integration. So let me show you this. It's going to be the same integral that we did last time, but let me show you the tabular integration way. I have 3 columns. One of them I just call sine, and that's just a plus minus pattern. And it goes as long as you need to, and we'll discuss how that works. There's going to be one part. This is basically like what you would make u for your first time, like we made u equal to x squared. And what happens is you keep taking the derivative of it, and that's precisely why the power of x keeps going down, is because when you take the derivative of the power of x, the power goes down. And then there's going to be another column that we call integral, and that's like the first thing that we made dv. Like for our first application of integration by parts, we did dv equals sine x, and so that's going to go here. Okay, so what do? Down the derivative column, I keep taking derivatives. So x squared becomes 2x. Derivative of that is just 2. And if with the power of x, if you keep going long enough, you'll get 0, because the derivative of a constant is 0. So of course, I could keep going, but it would just be zeros forever now. So I'm going to stop when I hit a 0. On this column, I keep doing antiderivatives. So antiderivative of sine is negative cosine. Antiderivative of negative cosine is negative sine. And I'm going to go down to where I'm across from the 0. So the antiderivative of negative sine is positive cosine. I had to think about that one, but we're good. Now here is what we do. I'm going to go like this. So I have a plus x squared times a negative cosine x. So put together, I'm going to write a negative x squared cosine x. And then I do another one of these where it's like across and then down. So like this. So I've got a minus 2x times minus sine, and the minus is canceled, so I write plus 2x sine x. And then here, so plus 2 cosine x. And then at some point you stop, and so I want to tell you the general answer. For us right now, I could just write plus c and I'm done. Like, notice that the answer that I just wrote down is the same as what we got. I just have to write plus c and then I'm done. That's because I went until I hit 0, but let me tell you in general what you do, because in general it's possible to use this in a situation where you're never going to hit 0, because it's possible that you would use this method when you're not dealing with the power of x. If you're dealing with the power of x, you're always going to hit 0, but you might not. what you do is, for the last row, wherever you decide to stop, you just go all the way across. So it's not like a cross and then down like this. It's just like all the way across. And so I would go minus the integral of this times this. So the minus comes from this, and then it's always the integral of this times this. Of course, in the situation we're in, this doesn't do anything. This whole thing is just 0. So this doesn't do anything. I just write a plus c and then we're good. So that's tabular integration. Right. Let's do another example. E to the x sine x. So let me walk you through this one. We are going to do integration by parts twice to this. And since we're going to do it twice, let's use the tabular method. So I guess if I'm going to do it twice, I'm going to need 3 rows. So let's talk about what to put here. Basically, what I would, oops, I got blurry. Yep, there we go. Okay. What I'm going to put here, this is like going to be your U. Like if I had to look at what I'm dealing with here and decide what to make U for my first application, that's going to go here, and my dV would go here. And so I'm thinking LIPTE. I don't see any logs. I don't see inverse trig. I don't see a power of x. Like I don't see x squared. Like I see x in the power, but each of the x I would call exponential. That's here. But okay, I'm going a little bit out of order because I'm supposed to pick the first thing that I see. For U, I see trig. So U should be sine x. That's the first priority for U. It actually doesn't matter too much in this situation, but this is usually good advice, so why not follow it? This is going to be the rest, so that's basically my e to the x, and so here I go. I keep doing derivatives, so cosine x, negative sine x. And here I keep doing integrals, so it's going to look like I'm not doing anything, but I swear I'm doing integrals. Okay, so what does this turn into? Well, so I go across and down, so there's going to be an e to the x sine x. Then there's going to be a minus e to the x cosine x, because I'm going like this, and then a plus, so now I'm on my last row, so I just go straight across, and it's an integral of this times this. And as usual, with integration by parts, we hope that the new integral is easier than the old one. And we are very upset and baffled, but this is going to actually go somewhere good. The new integral is basically the same as the old integral. I mean, it has a minus sign here, but that doesn't make it any more difficult or less difficult to integrate. So what are we going to do? So the nice thing about this is we just made a relationship between this integral and itself. We can solve this equation. So let me move this over here. So yeah, basically this has a negative sign on it, so when I move it over here, it's going to be positive, so it's going to be a 2. Okay, and then so I have this still here. And let me, okay, this is sort of a subtle thing, but let me start writing plus c. I was okay without a plus c here because there's an integral on both sides. Now that all my integrals are on one side, I sort of want this to be a plus c. And then ultimately I'm going to solve for the integral that I was interested in. All I have to do is divide by 2. And so we're basically done. What I wrote is maybe a little bit silly. Usually when I have an integral, I just write plus c. This has a c over 2. There's really nothing wrong with that. I could rename this constant. Instead of using c over 2, I could say I'll keep this part, and then instead of c over 2, I'll write like, I'll use the letter D just because it's the next letter of the alphabet, where big D is just c over 2. But the thing is, these constants could be anything, so it doesn't, it's sort of silly to just have a constant that could be anything and divide it by 2, because then you just get another constant that could be anything. Anyway, that's not a point that's really worth talking too much about, so let's call that our answer. So yeah, this is a trick that works for e to the x sine x. It also works for e to the x cosine x, and it works for similar things like I could put a 2 here or a 3 here or something like e to the 2x sine of 3x. This is a particular trick that tends to work for these things, where you do integration by parts 2 times, and that allows you to take your original integral and write it as an answer where the same thing appears again, and then you can solve the equation for it. Okay, let's do another one. Integral of arc sine x. So this one may throw you off. Integration by parts is usually, it's for when you see a function times another function. And I'm not getting that vibe from this at all. Of course, I can say this is times 1 or something, but why would I do that? This doesn't really jump out and tell me to do integration by parts, but integration by parts is still going to be successful. What are my priorities for u? I don't see any logarithms. I do see inverse trig. So u is arc sine x. dv, I always just say dv is the rest, but there's nothing left. So, of course, dx is always part of dv, but that's all it is. So dv is just dx. Or if I like, I can write 1 dx. Okay, so we're going to move forward with this. Derivative of arcsine, we have to remember. This is on the list of derivatives to remember. I will tell you what it is. The derivative of arcsine is 1 over 1 minus x squared. Okay. To find v, I'm doing an antiderivative of this. The antiderivative of dx is just, I mean, again, I can imagine that there's a 1 here. The antiderivative of 1 dx is just x, right? Okay, so I get u times v minus the integral of v du. And then I take a step back and I look at what I'm dealing with and I ask myself, is this new integral any better than the old integral, or would I know how to do it? And looking at this does not exactly fill me with joy, because it's not on my list of things to remember, but it's not that bad. Here's what we're going to do. I have to look at this and figure out how to integrate it, and it's not on the list. And but one thing that jumps out at me is maybe substitution, because I do see a composite function. I see the square root of not just the square root of x, but the square root of 1 minus x squared. And so if I'm thinking substitution, I would think that I would let w be 1 minus x squared. And now you can see, I mean, this is sort of a hint of like why I prefer to use the letter w when I'm doing a substitution, because I don't really want to use the same letter so much. Anyway, if I'm letting w be 1 minus x squared, dw is minus 2x dx. So I can solve this for dx. Like that. And let me pull one of these moves. I'm just going to work on this part right now. In the end, when I write my final answer, I'll have to include this, but let me just figure out what this is, and then I'll put everything together in the end. So this part is integral. This x, maybe I'm not too sure what to do with, so I'll just write x. This is 1 over the square root of w. And then dx gets replaced with what I got down here. And now, and this often happens, now I know what happens with this x, and I'm happy. All the x's just went away, so that's good. I don't want to see any x's. So what's going on here? I've got this minus 2 on the bottom, so I can write minus 1/2, and I can do that on the outside. And then this doesn't look so nice, but we're doing calculus, so it's good to remember that square root is the same as 1/2 power. And 1 over that gives me the negative power. So 1 over the square root is w to the minus 1/2. How do I integrate a power of w? I increase the power by 1, so now it would be positive 1/2, and then I'm supposed to divide by that. I prefer to multiply by the reciprocal, so whatever the new power is, I put the reciprocal in front, and this is times. Cancel. So I just get negative w to the 1/2, and let me go back and replace w with what it is. So I'm there. Let me put my final answer together, because I was here and then I took some time to work this out, but now it's time to put it all together. Final answer. X arc sine x minus whatever this turned into, which was this. So actually let me write plus 1 minus x squared to the 1/2. And I could turn this 1/2 power back into a square root again, but let's just leave it the way it is. And I should write plus c. right, good. Let me show you one more. We're going to learn a different way to do this integral, but I would like to show you this as an example of integration by parts because we can do it this way. This is an example where I am actually not going to follow LIPTE. Not exactly. Of course, if I were to follow it, I don't see any logs, I don't see inverse trig, I don't see a power of x, I see trig, so maybe if I was following this advice, I would let u be sine squared and then dv would just be the x, but that's not really what I'm going to do. U is just going to be one sine. It's not going to be sine squared, it's just going to be regular sine. dv has to be everything else, so dv is going to include the other sign. And of course the dx as usual. So here we go. du is cosine x. v, the antiderivative of sine is negative cosine. Okay, so this, here actually let me write this again. Sine squared x dx equals, okay, the formula for integration by parts is u times v minus the integral of v du. So v du, I've got a negative cosine times another cosine, so I can write negative cosine squared x. Okay, so here's where we are. Of course, I can pull this negative out, and that cancels that, so it's like a plus. Okay, so where are we? And in the end, we have to just hope that the new integral is easier than the original one. It's not clear that it is. I started with sine squared, and now I got cosine squared. It's unclear how this is going to work out. I mean, sine and cosine are like buddies. They go hand in hand. So fundamentally, it's hard to believe that integrating cosine squared is any easier than integrating sine squared. But look. Cosine squared is 1 minus sine squared. And I can take this apart because, of course, one of these things is very easy to integrate. Antiderivative of 1 is just x. And the other one is sine squared x. So we just did this strange thing again where I started with the integral of sine squared x. I come up with something that also involves the exact same thing, so let's solve for it. And by the way, this is still the same, like the left-hand side is still antiderivative of sine squared. So if I get this over, it's going to be 2 integral, oops, let me start that over. 2 integral of sine squared x equals this. And let me write plus c because I have all my integrals on the left, and then I will divide by 2. So and then let me do the same thing I did last time, where instead of c over 2, I'll write d. Like I said, in the next section, and actually we've already seen an example like this, it's possible to do this one differently, where you use a trig identity. But it's also okay to do it this way. And if you remember the trig identity, it's probably quicker to do it that way, honestly. But I just wanted to show you this as a strange example of integration by parts. First of all, because we don't follow the standard LIPTE advice. And second of all, because it's another example of this situation where I start with an integral and then I end up with the same integral and then I solve for it. All right.